So hello everyone. We continue with our analysis of stresses in bending, and we now move on to section 7.7, which is the stress analysis in bending, combined stresses. Okay, so we'll first see what these combined stresses are and then analyze them through some examples. So if one is interested in the possibility of yielding, okay, or fracture or a localized buckling, basically any mode of failure as such, it is necessary to examine the stress distribution in detail and to determine the state of stress at a critical points in the beam. Just take an example. I mean, if you have a beam of this sort, I mean, just okay, and then this is experiencing sort of combined loading, both the shear and the bending moment, shear force and the bending moment, and say if this is your critical point in the beam, you want to find the state of stress at this point. Okay, sigma xx, sigma xy, sigma xz, and so on, and eventually you want to transform this into the principal values and then use these principal stresses at this point in your failure theories. Okay, so by this time I'm sure you are aware of a few failure theories used, and that's what you want to do. So your course in designing actually starts from here, in the sense you should know what the principal stresses are, and then you put them into the failure theories and see whether failure has happened or not at this point, wherever this is acting. In this course we have studied how to arrive from a state of stress to the principal system. So there has to be a certain rotation along which the shear stresses would disappear, and you would only get the sigma 1, sigma 2, and sigma 3. Now to arrive at this general state of stress from here in the combined situation is what we want to do right now, okay, in this section. So this is what we intend to do. So let's see that through an example. Okay, so the example is 7.5. Now it is desired to investigate the state of stress at points B and C. This is the point B, this is the point C, in the top flange and the web of the I-beam. So this is the top flange, this is the bottom flange, this is a web. Okay, and when a shear force V and bending moment MB are being transmitted, so you have the shear force V and bending moment B on this I-shaped beam. Okay, so apart from the bending stress sigma xx, the nature of the shear stress at the web and the flange will be different. On the web it is tau xy, and on the flange it should be tau xz. Okay, so tau xz. So the reason, I mean, I think it should be very clear. You want to take the lengthier part of the beam. So for this web, the lengthier part is over, sorry, the lengthier part is over here, and for this flange, the lengthier part is over here. Okay, so that's why this happens, and I think we have seen this discussion about it in the earlier class. If you are not sure why this is happening, please stop the lecture right away and go back to this, do the derivations yourself, and then come back again. There is no point moving ahead with that incomplete knowledge. Okay, a bending stress sigma x is given by 716. So that would be equal to minus mb y by I z, and the shear stress tau xy is given by 7.25. So let's see what 7.25 was over here. That is or V minus V by I Z Z Y. Okay, this is how the shear stress would be. So this was 7.25, this was 7.16. Okay, and the magnitude of the tau xz is given by tau xz is given by, for this I-shaped beam, that is minus of VQ by T1 IZZ. Okay, so this is tau xz and this is because of 7.29. Okay, its sense is shown in the figure 7.17d. So you have MB which is shown, you have V which is shown, and then you want to find the sense of the stresses. So that can be seen over here, XZ and XY. Okay, so let's just remove. So sigma X is shown, sigma X is shown, tau XY and tau XZ. All of them are shown over here. So I think the sense of it is actually shown in figure 7.17a. Okay, 7.17d is okay. In 7.17 also you can see. So if you can check figure 7.17d, you can see the sense of this tau x y and tau xz. Anyways, the same has been shown in this figure 7.21a. Okay, so you have the same sense shown over here for all the stress. Now these stress components are shown in 7.21a. The Mohr circle for the stress drawn on figure 7.21b and c are constructed from these components. So remember, you have to have sigma x, you have to have tau xy, okay, and tau xz, and then you would be able to draw the Mohr circle. So if you consider point B, this one, it has a sigma x, it has tau xz. With that you have to find this Mohr circle. So you have to find sigma x like this. So it is clearly negative because it acts in this direction over here, and similarly tau xz will be acting in this particular way. So you have the xz formed, and okay, so there is no sigma y to start with. Okay, so that makes things quite easy. Okay, so if the sigma y was there, the point z would be displaced accordingly from the tau axis. Anyway, so you have this x and z points, and then you can draw the Mohr circle, and then you know how much rotation is required for this to convert to the 1-2 system. So currently it is in the xz system. You want to have a rotation so that you are in the 1-2 system, and 1-2 system is when you have the principal stresses sigma 1, sigma 2 and no shear stresses. Okay, so you would know how much of rotation is needed. It's 2 psi b over here, so it has to be a psi b on this side. Okay, so this has to be rotated by psi b. Similarly, for point C, you have sigma x and then you have tau xy. So sigma x is over here, the point x, and tau xy is acting like this, so it's positive. Okay, that's so in the previous case tau xz was negative, that's why it was point x was above the sigma axis. So this is the same convention which we learned earlier on, and this you would form to find xy, then give a rotation psi c over here for this to convert into the principal system. So that way you would have the values calculated. Okay, so okay, so this is constructed, and then you finally, using this and this, you are able to move to the principal stresses sigma 1 and sigma 2 at point B and C. To determine the most critical point in the cross section, it would be necessary to have a criterion for comparison. So it can be a yield criteria, fracture criteria, or buckling criteria. So fracture you have not read, buckling you have not read yet, fracture you won't read in this course, but you must have by this time learnt about yield criteria in your designing course. So you have to just plug in the values of sigma 1, sigma 2, and that. So yielding always happens at a point. So when you use this sigma 1 and sigma 2 into a failure or so-called a yield criteria, you will be only testing whether yielding happens at this point or not. The same happens over there. When you put this sigma 1 and sigma 2, you will be able to predict whether yielding happens at this point or not. Okay. So this is how you can do it in the most fundamental way, and then you want to compare and take whether failure will happen or not. Now this can be a lengthy analysis, clearly. I mean, converting from this to this and then finding the failure criteria, comparing it with the failure criteria is a lengthy analysis. Let's see what else is mentioned about this. In long slender beams, as pointed out in example 7.4, the greatest shear stress tau xy, remember we had done this question about tau xy max divided by sigma x max. The greatest shear stress tau xy, or okay, the greatest shear stress tau xy or tau xz, okay, or tau xz. So you know why tau xz would come in and where it would come in. So this would be an order of magnitude smaller than the greatest bending stress sigma x. Okay, so we have seen for a long slender beam, it was, so if L was greater than 10 times of H at least, it was an order of magnitude less the maximum shear stress. Okay, hence for many practical applications we can neglect the shear stress contribution, except we have previously noted for consideration for possible buckling. So buckling we'll see later on, and then you should come back to the I-beam buckling which we had left out. But for this application you can ignore the shear contributions. So shear stress contribution can be ignored, and once that is ignored, it's quite easy. You just have a sigma x which is there for you, and then uniaxial stress is very easy to put in a to check the failure criteria, because you have only one state of stress remaining. So a frequent type of loading in which a beam transmits a longitudinal force and or twisting moment in addition to the shear force and a bending moment. When there is a longitudinal force in addition to shear and bending, the analysis is similar to that outlined in section example. So this is what we would want to do in this particular analysis, example 7.6. Okay, so in figure 722a, you have an elastic circular shaft and it is transmitting a bending moment. Okay, bending moment. Please get a sense of how it is being built. Bent. It is transmitting an axial tensile force P, okay, and a twisting moment. Okay, it seems all of them are coming together. So this is a circular shaft which is being bent, it is being twisted, and it is being pulled. This is as grand as it can get in this course at least. Okay. Now in this case you want to study the state of combined stress under the action of all these three things. Okay. So let's see how we can proceed in this case. The problem represents addition of a bending moment to the loading condition considered in example 6.3. Okay, so if you go back to example 6.3, then you will have a twisting and axial loading but not bending. Over here we have added bending. Okay, that's the difference between examples. So let me see if it was actually example 6.3. Sometimes they misnumber seconds. Okay. Yes, it was example 6.3. So please go back to the torsion chapter and you can have a look at example 6.3. Okay, so we have the bending, which is in addition. So our method of approach is exactly parallel. In figure 722b, the individual stress distributions are sketched for the separate loads. Let's start with the easiest one. I always find the axial loading easy. Okay, so this is the first state of stress in which you have the tension, and then there is a uniform distribution of this force over this area, and that's why you have these little arrows. So this P can be equal to the stress over here can be sigma z, and that would be equal to P divided by the area, which is pi r naught square. Okay, now let's look at the twisting part. So we have seen before in chapter 6 that the shear stress in twisting tau theta z is like this. Okay, it is 0 at the center and it increases linearly as you move away from the center. So this is tau theta z is equal to mt r naught by iz, okay, at the surface, at the periphery of this, and at this surface essentially. If they are somewhere in the middle, that r naught goes away and then you are only left with r. Okay, and for the bending one, you would have a sigma z, okay, along the axial stress for that matter, that would be equal to mb r naught by ixx, sorry, r, okay, it should be r over here as well. R naught will be there, I mean, if you put r equal to r naught, but in general this is like this. Okay, so this will again be of this form, and right now this would become ixx, and yeah. Okay, so that's how these three stresses are given, the state of stress is given. Now that is shown in this figure. Now in C over here, you have written down these values and you have done that on the surface. So everywhere r will be replaced by r naught. Okay, and you show the individual stresses acting on an element at y equal to ra, at y equal to r naught. At this element, the distribution A and C have their greatest value, and that there is a reason why we are trying to do this at y equal to r naught. The reason is that this stress will be maximum at r equal to r naught, and this will also be maximum at r equal to r naught. Okay, so you want to, I mean, study anything from the perspective of design, you want it to get its maximum possible value. Okay, that's like the worst case scenario. So once this is done, you can basically say that this element over here, the same element, is experiencing the superposition of all these three individual contributions. Okay, so you have the shear stresses acting, so sigma z2 and sigma z1. Okay, and sigma z2 will also be equal to p by pi r naught square. Okay, that's how it has to be. And sigma z1 is the mean normal stress in the z direction, and in the axial direction, longitudinal direction, whatever you would want to call it. And then you have one shear component, so two normal and one shear, and this one shows over here two normals and one shear. So this is the total state of stress which you have, and since it acts only on a plane, there is no component along the thickness direction, it is a plane stress, since all the contributions of this are only on this plane. Okay, so once this is done, after that what you have to do, you have to plot this three-dimensional state of stress. So I'll just write it in a better way. You have sigma z1 plus sigma z2, sigma z1 plus sigma z2. Then you have a tau theta z, okay, then tau theta z, and then you would have a tau z theta and tau z theta. Okay, so you have this planar state of stress, and you want to convert it to the principal values, meaning you have 1, 2, 3, 4, and you want to convert it into sigma 1, sigma 2, 0, 0. Okay, so you want to first look at, so it has to be now in the theta z system. So the theta would be, this is an example which we I think did in lecture 14, the general state of stress. So that's what you would want to do over here. So you draw more circle, you will have a total of 3 circles, and you will have a sigma 1 and sigma 2. The maximum shear stress gives you the radius of this circle, that is tau theta z. Okay, how are you ensuring that this is the maximum shear stress? By taking r is equal to r naught over here. Okay, and that gives you the radius of the circle. Point theta and z you can have. So the normal stresses will be sigma z1 plus, so this is essentially what the normal stress is, sigma z1 plus sigma z2 equal to the sigma z. Okay, and fine. Now the theta angle will be 0 because there is no there is no component of stress over here. So this is 0 and this is also 0, and that's why you are at this axis over here. A similar thing had happened I think somewhere before as well. Yeah, over here. So once you have things in your theta z system, you would want to convert it to the 1-2 system, which is the principal system, and then you can find your answer. Okay, so this is how you would do this problem. Again, if you are not clear about how to draw this and how to come to this, please check lecture 14 or that discussion in chapter 4, which is stress in the generalized plane. Okay, let's now proceed to the last topic of this chapter, which is strain energy due to bending. And we get after the strain energy every now and then because it is very easy to use Castigliano's theorem and find the displacements at any point of interest. That's why we are trying to get into strain energy for bending. We have already done it for twisting and axial loading, but bending, if you add, then you can, I mean, if you have all the 3 loadings combined, you will be able to find a total strain energy, and then you can find a displacement values using Castigliano's theorem. That is the application in this course, and later on, perhaps at some point when you, if ever you take a course in finite element methods, you will see that theory of finite element methods very heavily relies on the energy and the complementary energy which you have learned before. Okay, so the strain energy in a linear elastic body subjected to an arbitrary distribution of stress and strain is given by by equation 517. So in this section we specialize only to the beam subjected to bending. Okay, we will not go into the general case yet. So according to equation 517, the total strain is equal to half into, you will have a sigma x ex dx dy dz, or for a linear elastic solid, sigma x square by 2e dx dy dz. So the integration is over the entire volume of the beam, that's obvious, and you want to substitute now 716. 716 is minus mby by izz, You want to make that substitution over here. Okay, and so first of all, from 517, you will only notice that one term comes out of it, which is this one. Despite the fact you can have other terms, the product sigma x and epsilon x must be there. For example, tau xy and tau xz and other such terms would also be there. But why are they not appearing in this case? Okay, why are they not contributing to the energy? Can you think of a reason? Can you see what the values of stresses and strains are? Okay, and see that, and then perhaps get to an answer. Anyways, for this you just convert sigma x over here, and then u would be equal to, you put the sigma x over here, and then u would finally be equal to length of the beam mb square 2ei zz dx. Okay, so izz is again the second moment of inertia, and the mb is the bending moment, so there's no issue at all. And we are not referring to pure bending now. Okay, we are referring, because this we had found was exactly true even when the shear force was present, and it was constant, and it was approximately true when the shear force was present and not of a constant value. Even then this was approximately true, so we have used it over here based on our engineering theory. So this formula may also be derived by, you have this differential method of energy as well. So let's see how that works in this case. So consider a length dx of this differential element, and it acts as a bending spring. If in figure 7.24 the final values of the bending moment and bending angle are mb and d phi, respectively, the work done during the loading process and which would grow. So you have, it's, if you consider it like a spring, you would have du is equal to half into mb into d phi. Okay, this is the angle d phi, and this is what you can write as half into mb d phi by dx into dx. So when figure 7.14 is substituted for d phi by dx and the result is integrated over the length of the beam, we obtain 7.31. So once you integrate this over the length of the beam, you should be able to get this equation. Okay, and fine. So what could you substitute? Let's look at 7.14 before we sort of. So 7.14 was basically the relationship between d phi by ds is equal to 1 by rho equal to mb by e I z z. So basically a relationship between the curvature. This was happening in section 7.5. It was equation 7.14. So you have to use this over here. Okay, please do this and don't leave this. Don't just substitute ds is equal to dx and solve it. Please see that if all of it makes sense. Okay, so when a beam is subjected to transverse shear in addition to the bending, okay, so that's where I was telling you that in reality you cannot ignore this. Okay, and the reason why we could write this, and it was not exactly, oh, it was actually written in your book that this was for pure bending only, but you will see the magic soon. So okay, if you do have shear transverse shear components tau xz and tau xy, you have half of sigma x epsilon x plus tau xy gamma xy plus tau xz gamma xz, and then dx dy dz, and you would be able to then finally be able to write that this will be equal to, over the entire volume, sigma x square by 2e dv plus over the entire volume, tau x square plus tau y xy square tau y tau xz square. Okay. So in reality, you do take it. For this was for pure bending, and that's why we had ignored this. So that was the reasoning over there for the Hooke's law when we were sorry, in equation 5.17 when we were trying to write. Okay, so the first integral on the right is identical to the form of strain energy in pure bending. So this is like pure bending contribution that is visible over here. Okay, actually over here. The second integral is the contribution to the strain energy due to the transverse shear stresses. Now let's see. For slender members, the latter contributions is almost always negligible in comparison with the former. So these values we have seen, the maximum of this value is negligible for a slender beam. Hence it is okay to ignore this. Okay, if sigma x is an order of magnitude larger than tau xy and tau xz, then since the integral is dependent on the squares, so if tau xy and sigma x of this is greater than, this is smaller than 1, the square of this will be much smaller than 1. Okay, so this is what happens, and then you can neglect the contribution. The pure bending formula is then used to represent the total strain. So U is equal to sigma x square dV by 2E is used for all cases, even when the transverse shear stresses act. Okay, or it was not a pure bending, so it is valid approximately even in general bending. Okay, so this is what we have, and you want to see an illustration of how that works. So I don't think we, okay, so you can see how you would want to draw. So if you look at figure 7.19, let's see figure 7.19. So you want to use UU in example 7.4. Okay, so you have to go to figure 7.19, the beam which was supported at the ends and load was applied. So you want to write the bending moment, and you will be using the singularity functions. Okay, so you will get a contribution due to bending, you will get a contribution due to shear, and then you can compare them and see that how they compare with each other. So that is what is done in the later part of this, but I think it is good time to actually revise your ability to use singularity functions. Okay, so please do that the way it is done before in your textbook. So you have equation 7.33, 7.34 and 7.35 will discuss all this. So this is where we can sort of stop our discussion so that you can work the remainder part out of section 7.8. And beyond this, we do not do things in this chapter just because I think they are better suited to be done in your designing course rather than over here, because they are mostly related to theories of failure. What we do now move to is the deformation due to bending. So until now we have done the stresses due to bending, but right now we want to study the deflections due to bending. If there's a beam, how much would it deflect, or how would it deflect in bending? That's what we want to do now. Okay, so let's sort of set up our motivation for this. So we consider deflection of slender members yet again, which transmit bending moment. Okay, and there are many practical design problems in which the deflection considerations are of great importance. When you have high speed machinery with close tolerances, everyone is aware of how do tolerances play a role in fitting of parts into an assembly in a machine. Every one of you should be aware. So if you have excessive deflections anywhere, then they can cause interference between moving parts, and then you will have these you will have wear of those parts. Soon the surfaces will come into contact, and then they will cause wear. So this is what we want to study over here. Can we control the deflection due to bending? Just like we wanted to control or study the stresses due to bending, if this is the bending moment acting, what is the stress which is acting across the beam? And through that we will you convert it to the, at critical points we would find the state of stress under the combined action of bending, twisting, and axial loading. Then those state of stress would get converted to the principal values, and then those principal values can be used in failure. Now there are other reasons when the material may not actually fail due to stress, but it may become so deflected that it is not serving the purpose which it should. Okay, so I mean, think of the, say, axle of the shaft of a car. So this is the front, this is the back, car is moving ahead like this. Now if this particular shaft which is transferring, so this is your IC engine, and then you have the motion which is happening over here, the rear wheels. We have seen that mechanism, I think, somewhere in chapter 6 or 7, I'm not sure where, in chapter 6 in torsion. Now if this particular thing which you have, which experiences both torsion and bending according to your figure 6.1, if it becomes like this, okay, despite it not actually failing stress wise, this is still bad, because you cannot allow your shaft to be like this. I mean, it will start touching parts of the machine which it should not normally be in contact with, and then this will wear, and then this machine will not be usable anymore. So it is not just the stresses which we must consider, but also the deflections. And there are some other examples given in 8.1 in your book. You have to look at videos or pictures to understand exactly what they mean. For example, there are leaf springs, okay, and they are leaf spring has already come before one, so I think you should definitely take a look at a video of what a leaf spring is. Okay, and then on the other hand, you should also see the limit deflections in structural framework of buildings. So limit deflections, I mean, how much of deflection should happen in structural framework of buildings. Okay, so if this is, say, the steel framework of a building, and this is a beam, this is a beam, this is a beam carrying the load above it, then you cannot allow it to deflect it to an unusually high amount. So it must be deflecting in a certain range which you think is reasonable, despite the fact that it may not actually fail due to stresses. That is what motivates us to study why we should care about the bending of a beam. Okay, so the determination of the bending deflection, like all other the problems considered in this book, involves first the selection of a model, which is to represent the actual physical member, and then the model for the analysis of the beam. The model for the analysis of the beams was first introduced in chapter 3. In chapter 7, the local distribution and the stress distribution across the section of a beam were discussed in the last one. We did not, however, evaluate the overall deformation of the beam. What we did was, we took a beam, then we took a point of our interest. This beam, or I mean, you can look at an eye-shaped beam, whatever worked for you. And then we took certain critical points on it, say over here and then over here, and then we found out, say, the stresses and the strains at these points. We never worried about how this beam, this eye-shaped beam, will deflect overall, and that is what we want to in this chapter. Okay, we were in the local situation early on. What we did was, we took a cross section, and then we were trying to find the stress field, whatever the point of interest was, we used to cut a plane and find the stresses and strains over there. Now we want to find the overall deflection, and uh, we come back to the same method which we have done before, which was 2.1 again. Equilibrium, deformation and compatibility, and relationship between stress and strain. So this time we'll be seeing the statically indeterminate beams. Remember the indeterminate, statically indeterminate beams in which the stresses alone were not enough, or the forces alone were not enough in trying to find to solve the problem. So we required this word of statically indeterminate situation, and that's what we would intend to do. So that is what we want to start off with. So let's see the terminology of this over here. Okay, so when you have a symmetrical linear elastic beam, remember the symmetrical, the plane of symmetry was there, and then the cross-sectional area was symmetrical about that. So there you have to have a symmetrical linear elastic beam is subjected to pure bending, and we always start with this because this makes life easy. Okay, and it is shown in figure 8.1 for us. The curvature of the neutral axis is related to the applied bending moment. So this is something which we had done in the last chapter, but it is a good time to actually revise it. I think it was 7.17 if I am not mistaken. Okay, but you can check. But this was derived in chapter 7. The relationship between curvature and the deformation and the bending moment. Okay, so you have MB over here, you have MB over here because it's pure bending, and this was your neutral axis, this one. Rho is your curvature, delta phi is this angle formed by the two parallels, and this is your neutral surface, this one. Okay, and delta S is equal to rho into delta phi. This is because of its circular arc, or any arc for that matter. You have this, and as delta S tends to 0, delta phi will be like this. And I mean, if you recall, there was this point O and O dash, and the case was made that if delta phi is too small, this O dash will overlap. So I think that all is already taken care of in this. So please look for the equivalent figure of chapter 7 in this case, and I can tell you what that figure was. That was figure 7.3. Please revise this, and then this equation was, I think, 7.17. No, it was 7.14. So this was equation 7.14. So please revise this before we move ahead. One of the things is that we would want to maintain this exact orientation throughout this chapter. This orientation, just so that the development of the theory is consistent throughout, and the long dimension of the beam will always be in the x direction. Okay, and the bending will happen in the take place in the xy plane, usually about the z axis. Okay, so about this axis the bending is taking place, and under these circumstances it will cause no ambiguity if instead of the symbol IZZ we just use I. Okay, so rather than IZZ we will just be using I, because we will follow the same diagram, this particular diagram, throughout our chapter. Okay, so moving ahead, we want to find the curvature of the neutral axis completely defines the deformation of an element in pure bending. So for an element this was done already. Now we want to extend this to the case of a general bending where the bending moment varies along the length, right, MB of x. We make a simplifying assumption. We assume that the shear forces which necessarily accompany a varying bending moment do not contribute significantly to the overall deformation. This is an assumption and a new assumption. Please don't treat it like an assumption you have already seen or known before. No, it has never come before until now, and it's a very new assumption. The shear forces which necessarily accompany a varying bending moment do not contribute significantly to overall deformation. The language and the words are very clear. Overall deformation mean not this localized deflection, but the overall deflection of the beam. If for a straight beam, bending is happening, the overall deflection. Okay, so this is the assumption which we take in this course in this course for this objective of finding the overall deflection. So thus we assume that the deformation is still defined by the curvature and that the curvature is still given by this. Okay, and because the shear forces do not contribute significantly to the overall deflection, and if we know the bending moment varies along the length of the beam, we will then know how the curvature varies. So the fun part about this is that this derivation, it was fine that MB was a function of X. Okay, so in this case, if you can find out what MB of X is, you can perform some integration and then find out this delta phi by delta S or d phi by ds, and we'll see that how that relates to the overall deflection. But this lies, the key lies over here. Okay. So let's see how that can be done. I mean, how can we find the deflection of a beam? In this case, so we start with the definition of the slope of a neutral axis. So let's see figure 8.2a. This is the beam and it was originally straight clearly, and now it has deflected along this dashed geometry. So you start off with the slope. Let's see, we can write dv by dx is equal to tan phi. Okay, so y is this, x is this. Okay, so dv by dx is basically the change in this direction, like up, it's going up now. Okay, and the change dv which will happen over a distance dx. So the change dv happening at this point over a distance dx, and that will give a phi. So tan phi will be equal to this value, and you want to differentiate with respect to the arc length s. So that would be d2v by dx square into dx by ds, and that would be tan phi differentiated would be 6 square phi d phi by ds. Okay, and once, and you should also be able to now visualize this in the xy plane. So in the xy plane, dx and dy are like this, and the surface, I mean the change in the arc length will be ds. Okay, so originally s may have been like this, and then ds has happened over there. Okay, so the curvature d phi by ds, okay, is d2 v by dx square dx by ds cos square phi. So you have just used this, I mean cos square phi has been inverted, and you can write d phi by ds as this value. And now figure 8.2b over here, you look at this, you want to write cos phi is equal to b, which is dx by ds, base by hypotenuse, and this ds can be written using the hypotenuse of a right angled triangle as 1 plus dv by dx whole square 1 by 2. Okay, this implies that d phi by ds is equal to d2v by dx square by 1 plus dv by dx whole square 3 by 2. Okay, so you have found this, and it is actually v, which is the deflection which you are looking for. Okay, that is how the deflection of the beam is, v. Okay, now you want to substitute this d phi by ds over here, and that would give you the relationship between the bending moment and the deflection. So you want to substitute this 8.2 into 8.1. The reason was that the curvature still determines the deflection because the contributions due to shear forces are insignificant. So you obtain this differential equation, which is once you substitute this into this, you would get a d2v by dx square by 1 plus dv by dx whole square into 3 by 2 and mb by ei. So let's leave it over here in this class, in which we have arrived at this differential equation. Perhaps in the next class we'll continue with this topic and move ahead by taking certain other approximations. So let's see how that plays out. Thank you.